Okay, we're going to try again. Thursday class, take two. We got bumped off of the live stream. So today we're going to talk about experimental and theoretical probability. I'm going to finish the examples for lesson one. We stopped yesterday just discussing the idea of probability and the definition of probability. So probability is the prediction. We're making predictions that an event will happen, right? So we don't know probability. We don't know for sure if our prediction will be accurate or not, but we're making the best bet, right? The best judgment using the available data. So we're making predictions when we use probability to the best of our knowledge, but we also know that there's not, we don't know for sure if an event will occur. There's this element of chance when we're talking about probability, and that's why there's two types of probability, experimental and theoretical. Okay? And you should know the difference because that's a huge deal with probability. We know that probability we're trying to make predictions based on best data and best information given, but it's just prediction. We don't know if it's actually going to happen. So experimental probability refers to the probability that's based on past events to predict future events. These past events can help you extrapolate information about what might happen in the future. For example, that's how we predict what the weather will be, right? The weather people use previous weather data to predict what the weather will be like. It's called the experimental probability. I'm going to define it another way. This is what actually happens. Okay, and theoretical probability refers to using possible outcomes to predict future probability. There does not need to be any past events to calculate theoretical probability. So this is what should happen. Based on past events. Okay, so experimental is after the experiment is over or after the event has taken place. This is what actually happens. Theoretical probability is what should happen. So let's see what this is like because there's two types, right? What we think should happen and what actually happens. Amina has a six-sided cube and each face is labeled with a different number. So of course they're talking about a die, right? Like a dice that you roll in kids games and stuff. So it's just one of these guys, right? If you've ever, and they usually have a little dot, and then there will be a side with two dots, and then a side with three dots, right? And there are six sides to the die, so each side has a different number of dots, and they include 1 dot, 2 dot, 3 dot, 4 dot, 5 dot, 6 dot, and that's how we label the sides. She tosses the cube 8 times and records the following results. She rolled a 6, a 3, a 4, another 6, a 1, a 5, and a 6. State the experimental probability of tossing the cube and it's showing 6, okay? So this is what actually happened, okay? What actually happened is, okay, how many 6s did she get? 1, 2, 3, 4. She got 4 6s out of 8 tosses. So I'm going to just label these. This is the actual number of 6s rolled. This is the actual total number of rolls, like rolls of the die. State the theoretical probability of tossing the cube and it's showing 6. Okay. The theoretical probability of rolling a 6 is, okay, it's just 1 out of 6. And that is the number of sides with 6 dots. And this is the total number of sides. Okay, there's only one side of a die with 6 dots, and there's 6 sides in total. So the actual theoretical probability is only 1 out of 6. But she actually rolled 6s half the time. All right, let's do example 5 to kind of further nail this concept in. There are 4 red marbles, 3 blue, 2 yellow, and 1 green. Marcel chooses a marble out of the bag and then replaces it each time. So that means he's got this bag of marbles. He's just dipping his hand in with his eyes closed or not looking into the bag. He's dipping his hand in, picking out a marble, and then he's just making a note of the color. So he does this 5 times. That's important to note. He chose the following numbers on his 5 draws. He got a green, then a blue, then a yellow, then another green, and another yellow. Express the experimental probability of choosing a green, right? This is what actually happened. And I know it sounds funny, but his drawing the marble out of the bag is called the experiment, right? It's not a big scientific experiment, but the experiment is what the person was actually doing in the situation. So this guy was dipping his hand into a bag of marbles. That is called the experiment. So experimental probably is what actually happened. And this theoretical is what should have happened. Okay, let's see what actually happened. He got, so I'm going to introduce some new symbols. When you're asked to find the probability of choosing green, one of the ways you can tell your reader you're talking about probability, the capital P stands for probability. So the probability of rolling a green equals, I'm just kind of supplying a little more info this time when I record my answer. All right, so what happened here? He got 2 greens out of 5 tries, right? So this is the number of green marbles chosen. Total number of marbles chosen, right? Because he selected in total 5. All right, what should have happened? Well, let's see. What should have happened is initially he had 4, 7, 8, 9, 10. Probability of getting a green theoretically, he had 10 marbles in the bag and he had only 1 green. So in theory, he should have gotten, there was less of a chance for him to pull a green marble than what actually happened. Number of green marbles in the bag. And this is total number of marbles in the bag. All right. Okay. Let's see so hopefully these concepts are becoming a little more familiar to you. Let's flip over and finish the last couple of examples. So let's do this. At the top, it says it's important to note that for a large number of trials in an experiment, so a large number of coin tosses or a large number of choosing marbles, the experimental probability begins to approach the theoretical. Let's try this next example. Bindi tosses a coin 10 times. She records her findings. She got 9 heads and 1 tail. State the experimental probability of tossing the coin and it landing heads. Well, the probability of getting heads, if I look to what her experiment shows, she got 9 heads, right? 9 heads, 10 total coin tosses. State the theoretical probability. Well, in theory, the probability of getting heads on a coin toss, since there's only 2 sides to the coin and one of them is heads, this is the number of heads. And this is the total number of sides to a coin. There's only 2 sides to a coin. There's only 2 ways it could end up, either heads or tails. So there's actually a 50% chance of her getting a head. On her experiment, there was a 90% occurrence of heads. What would happen if Bindi tossed the coin 20 times, 100 times, 1,000,000 tosses the coin? The closer the experimental probability gets to 50%. Okay, so this actually, remember, 9 out of 10, if I just convert that to percent, that's 90% heads. That's what the percentage would, that was what the probability would be in percentage. And then 1 out of 2 times 100 is 50% heads. In theory, that's what we expect to happen. What happened in her one little experiment, like she tossed it 10 times, that was her complete experiment. She got 90% heads. What would happen is if she tossed the coins 1,000,000 times, this probability would drop down to 50%. Over repeated trials, what actually happens becomes closer and closer to what should happen. So that's interesting. That's why, this kind of explains why, if you know of anyone who has a large family, for example, they might have 6, I've heard of this before, they might have 6 children in their family and they're all girls or they're all boys, right? 100% of their children are all girls or all boys, and you would think, oh, that's really strange. You would expect, what probability tells us is that in a family of 6, 50% would be girls, 50% would be boys. But sometimes it happens that 6 out of 6 kids are girls. So that's quite interesting. But if you look worldwide at our population, which I don't know what the population of the world is, it's in the billions. If you look at the worldwide statistics, it's almost 50-50. Like it might be 49-51 right now, but pretty much it's 50-50, 50% male, 50% female. That tells you that over repeated trials, as the data sample, the sample of data gets larger and larger, the actual probability, the experimental probability, gets closer and closer to theoretical. Okay, and this is kind of interesting. If you want, you can visit this site. I'll show you what it looks like. I have it loaded, I think, on this little tablet. Let's see if I can find, okay. So I just went to this website. So btwaters.com. And if you go to, let's see what I can find it. Here, we'll just do this. See if this shows up on the website. So if you go to the website, you'll see this. This is, I'm not sure if he's a mathematician, but he's got a bunch of games on the website, and this kind of shows you how theoretical and experimental probability work. So I looked for, where was it? Probability games, sorry. Can math be fun? Of course it can. So he's got some, you can try a dice roll. We just did the dice roll. If you do the coin flip, okay, it talks about a coin has two sides, heads and tails. When you flip it, what are the chances it comes up heads? What are the chances it comes up tails? Assuming the coin is not tainted, that means like a trick coin. It has an equal chance of coming up on either side. Therefore, it should come up heads 1 out of every 2 times, or 50%. And it talks to you about what should happen. So if we do playing the game, okay, let me try. So something's, here we go. So let's play the game. So it's pretty teeny tiny. I'm going to kind of scooch down a bit. You can see what's happening. Okay. So if you look here, let's just do this. It just says it's going to toss the coin 5,000 times. So actually, let's change this. I'm going to change it to, I'm going to toss the coin only 20 times. And then we're going to go auto flip. Now the expected is 50% 50%. Oh, let's just do the session. Sorry. So on my coin tosses, the first 20 tosses, down here it says we got 7 heads and 13 tails. Okay, that's interesting. We got 35% heads, 65% tails, so more tails. Let's increase this to 100 tosses. Okay, see how all of a sudden we got ours, like we went, the 120 means we did 20 first and then 100. So we got 59 heads, 61 tails. You can see how my percentages are getting closer to 50-50. Let's do 10,000 coin tosses now. It's basically, if you round it, it's 50-50. So it's just kind of interesting how probability works. But that doesn't mean, even though you think it should be, it's still pretty hard to predict on the next coin toss, right? Whether it's going to be heads or tails. So that's sort of the mystery of life too. Even though you think you know what's going to happen, you can't say for sure. All right, so I think that's it for all you need to know to assign it. So I'm going to assign the rest. It's quite a large assignment. I'm going to assign the rest of assignment 1, and I will do a couple of these tomorrow and give you maybe time to work tomorrow. To try and do as much as you can on assignment 1 before tomorrow. And then we'll meet again and we'll talk about any questions you might have had on assignment 1. So that is it for the day. And it looks like it's getting sunny out. So maybe you could go out and enjoy a bit of the sunshine. Talk to you later.